Section 14.3, the rate law, the effect of concentration on rate. One way of studying the effect of concentration on reaction rate is to determine the way in which the rate of the beginning of the reaction, or the initial rate, depends upon the starting concentrations. To illustrate this approach, consider the following reaction. Ammonium ion plus nitrite ion yields nitrogen plus water. We might study the rate of this reaction by measuring the concentration of either ammonium or nitrite as a function of time, or by measuring the volume of nitrogen gas collected. Because the stoichiometric coefficients on ammonium or nitrite and nitrogen are all the same, all of these rates would be equal. Table 14.2 shows the initial reaction rate for the various starting concentrations of ammonium and nitrate. These data indicate that changing either the ammonium or the nitrate changes the reaction rate. Notice that if we double the ammonium while holding the nitrate constant, the rate doubles. Compare experiments 1 and 2. If ammonium is increased by a factor of 4 with the nitrate left unchanged, compare experiments 1 and 3, the rate changes by a factor of 4, and so forth. These results indicate that the rate is proportional to ammonium. When nitrite is similarly varied while ammonium is held constant, the rate is affected in the same manner. Thus, the rate is also directly proportional to the concentration of nitrite. We can express the way in which the rate depends upon the concentrations of the reactants, ammonium and nitrite, in terms of the following equation. The rate is equal to some constant K times the concentration of ammonium times the concentration of nitrite. An equation such as equation 14.6, which shows how the rate depends upon the concentrations of the reactant, is called the rate law. For a general reaction, A moles of A plus B moles of B yields C moles of C and D moles of D. The rate law generally has the form of rate equals some constant times the concentration of A raised to the m power times the concentration of B raised to the n power. The constant K of the rate law is called the rate constant. The magnitude of K changes with temperature and therefore determines how temperature affects the rate, as we'll see in section 14.5. The exponents m and n are typically small whole numbers, usually 0, 1, or 2. We'll consider these exponents more closely very shortly. If we know the rate law for a reaction and its rate for a set of reaction concentrations, we can calculate the value of the rate constant K. For example, using the data in table 14.2 and the results from experiment 1, we can substitute into equation 14.6. 5.4 times 10 to the negative 7 moles per second equals the rate K times 0.01 moles times 0.2 moles. Solving for K gives us 2.7 times 10 to the negative 4 per molar per second. You may wish to verify the same value of A is obtained using any of the other experimental results given in table 14.2. Once we have both the rate law and the value of the rate constant for a reaction, we can calculate the rate of reaction for any set of concentrations. For example, using equation 14.6 and the rate constant of 2.7 times 10 to the negative 4 per molar per second, we can calculate the rate for ammonium equals 0.1 molarity and nitrate as 0.1 molarity. The rate equals 2.7 times 10 to the negative 4 per molar per second times 0.1 molar times 0.1 molar equals 2.7 times 10 to the 6 molarity per second. Reaction orders, the exponents in the rate law. The rate laws for most reactions have the general form rate equals some constant K times reactant 1 to the m power times reactant 2 to the n power, so on. The exponents m and m in the rate law are called reaction orders. For example, consider again the rate law for the reaction of ammonium with nitrite. The rate is some constant K times the concentration of ammonium times the concentration of nitrite. Because the exponent of the concentration of ammonium is 1, the rate is first order in ammonium. The rate is also first order in nitrite. The exponent 1 is not explicitly shown in the rate laws. The overall reaction order is the sum of all the orders with respect to each reactant in the rate law. Thus, the rate law has an overall reaction order of 1 plus 1 equals 2, and the reaction is second order overall. The exponents in a rate law indicate how the rate is affected by the concentrations of each reactant. Because the rate at which the ammonium reacts with the nitrite depends on the concentration of ammonium raised to the first power, the rate doubles when the concentration of ammonium doubles, triples when the concentration of ammonium triples, and so forth. Doubling or tripling nitrite likewise doubles or triples the rate. If the rate law is second order with respect to the reactant A squared, then doubling the concentration of that substance causes the reaction rate to quadruple. So 2 to the squared equals 4, whereas tripling the concentration causes the rate to increase ninefold. 3 squared equals 9. The following are some additional examples of rate laws. 2N2O5 yields 4NO2 plus O2. The rate is K, a concentration of N2O5. H3Cl3 plus Cl2 yields CCl4 plus HCl. The rate is K, concentration of CHCl3 times the concentration of Cl2 to the 1/2 power. H2 plus I2 yields 2HI. The rate is KH2I2. Although the exponents in a rate law are sometimes the same as the coefficients in the balanced equation, this is not necessarily the case, as seen in equations 14.9 and 14.10. The values of these exponents must be determined experimentally. In most rate laws, reaction orders are 0, 1, or 2. However, we can occasionally encounter laws which the reaction order is fractional, such as the equation 1410, or even negative. Units of rate constants. The units of rate constants depends on the overall reaction order of the rate law. In a reaction that's second order overall, for example, the units of the rate constant must satisfy the equation units of rate equal the units of rate constant times the units of rate concentration squared. Hence, in other units of concentration and time, units of rate over units of concentration squared equals molarity to the -1 seconds to the -1. Using initial rates to determine rate laws. The rate law for any chemical reaction must be determined experimentally. It cannot be predicted by merely looking at the chemical equation. We often determine the rate law for a reaction by the same method we applied to the data in Table 14.2. We observe the effects of changing the initial concentrations of the reactants on the initial rate of the reaction. We have seen that the rate law for most reactants have the general form of rate equals K times reactant 1 to the M, reactant 2 to the N, so forth. Thus, the task of determining the rate law becomes one of determining the reaction orders M and N. In most reactions, the reaction orders are 0, 1, or 2. If a reaction is 0 order in a particular reactant, changing the concentration will have no effect on rate, as long as some of the reactant is present, because any concentration raised to the 0 power equals 1. On the other hand, we have seen that when a reaction is first order in a reactant, changes in the concentration of that reactant will produce proportional changes in the rate. Thus, doubling the concentration will double the rate, and so forth. Finally, when the rate law is second order in a particular reactant, doubling its concentration increases the rate by a factor of 2 squared, or 4. Tripling a concentration causes the rate to increase by a factor of 3 squared or 9 and so forth. In working with rate laws, it's important to realize that the rate of reaction depends on concentration, but the rate constant does not. As we'll see later in this chapter, the rate constant, and hence the reaction rate, is affected by the temperature and by the presence of a catalyst.